Okay. Thank you, Ivan, for the introduction. I'll talk today about action recognition in videos. So first of all, what are actions? Actions can be, for example, short actions such as answering phone or handshake. But what people are interested also are birthday parties, or some people also want to find videos of grooming an animal. So this would be videos on YouTube. So if you're interested to find specific or generic videos on YouTube, that would be the task to search for them. Okay, and so what are the tasks in action recognition? So first of all, classification. So you have given a video clip and you want to see what's in there. So here, for example, you would have a clip. The girl is making a sandwich, but it's not feeding an animal. This can be used for search, for example, on YouTube. But then if you want to analyze more finely what's going on in the video, you have to really localize where and when the specific event is happening in the video. Okay, and so here an example of what you want to do. You want to see where the person is and what's the object he's manipulating. Okay, and why do we want to do this? Obviously, there's a lot of video data available today. You all know this. And people want to search for this content. And often there are not many keywords, or the keywords are not completely appropriate. So we want to use visual cues as well for search. And then people also want to have a very clear idea what's going on. So for example, if you have, how do you make a pizza? You want to see what's happening there. And then maybe the most important application today are for self-driving cars and video surveillance. So self-driving cars, you want to see what's going on, what are the other cars on the road, what are the humans doing, are they running towards the street or not. And then in video surveillance, you want to interpret the behavior of the crowd, you want to see if somebody is putting an object down, if he's misbehaving, is doing some specific actions. Okay, so these are all very important problems. And so what are those challenging? Why is it difficult? So there are large changes in viewpoint appearance, interclass variation, and camera motion. So here, for example, if you look at the viewpoint for these two classes, eating, you can see actually that there's a lot of viewpoint change, and the appearance and the interclass variation is very strong. So if you want to recognize here that in the two cases somebody is eating, it's very difficult. Another example, so here again, an eating example. And then here you can see that another problem is camera motion. The camera can move significant, so you have to dissociate the camera motion from the motion of the actors. Okay, and then another problem is that the manual collection of training data is difficult. For many actions, they occur only very rarely, so it's difficult to obtain data for them. And it's also very difficult to define a good action vocabulary. So today we can detect activities, but it's really hard to say what's the corolarity for an action and how to present composite actions. Okay, and then people also work on action recognition from still images, so you can actually extract the human pose and the objects. But of course, if you have motion information, it gives you an additional cue. So for example, if you want to see if somebody is opening or closing the door, sitting down or standing up, you really need motion. And actually, motion is in many cases sufficient by itself to disambiguate the action. So here, this was one of the studies by Johnson to see how people actually perceive motion. And you can see here very clearly that you see that this is a male walking. So you can really just from this very sparse representation already interpret what the action is. So motion is also necessary to see what the action is. Okay, and so in the following I'll present different works in action localization. So the first one, so I'll here concentrate on spatial temporal action localization, as that's the more difficult problem today, and it's also more relevant for many applications. So the first approach is based on frame-based spatial temporal action localization. So these are the state-of-the-art approaches. So what is it? You want to localize where the action starts, how long it lasts, and who's the person performing the action. So for example, here you can have 2 people drinking, so you want to say both of them are drinking and not just only one. So you really want to annotate every person with the relevant action. And so today's state-of-the-art approaches, they are based on the same idea. What they do is they train action-specific CNN detectors, so basically on a frame level. So on a frame level, you have this CNN-based action classifiers. Then you have different ways of linking these detections over space-time, either by tracking or by just simple dynamic programming with linking. Once you have these tubes, you score them with different mechanisms and employ a sliding window approach. Okay, so here in detail, how do you localize the action in each frame? So you have proposals, for example, edge proposals, or we'll see in a minute different types of proposals. Then for each of these proposals, you extract features. What's different here from still images, you have features of the appearance, and you have features of the motion, optical flow cue. So optical flow measures how much the person is moving from one frame to the other. This gives you a flow field. This flow field you can see here, it's the color-coded flow field. And so what you do is you extract features from the appearance and from the flow. You merge them together, train a classifier on top of this, and this gives you an indication what is the action performed in a box, or is it just the background. Then you can link these detections together, and then you apply a tempo sliding window classifier to see where exactly in this linked tube the action is performed. Okay, because basically what it will do, it will detect it for the whole video clip, and then what you really want to say is in which moment of time, for example, the person is shooting the basketball into the net. Okay, and then so recently there's a whole line of work exploring different types of approaches to extract these features. And so here, another approach which gets actually state-of-the-art performance today is based on the faster Arsenic detector. So what is the faster Arsenic detector doing? It learns proposals, and for each of these proposals, you extract features. And so here, basically, again, we use the idea that we combine appearance and flow features. Here we use multiple flows stacked together. And then we can extract proposals from both streams, so here from the appearance stream and here from the flow stream. We can then pool all these proposals together, and from this pool of proposals we extract the features, which we concatenate and classify them, and we can use them then to score each of the boxes. And so here, what's the advantage? The advantage is that the proposals are learned specifically to the actions, so we don't have any generic proposal mechanism, but they're specific for the action. We learn them from appearance and flow, so basically if a person is not moving or difficult to see, you can extract it from the flow. And then you have these 2 types of features which you combine. Okay, so what are the current state-of-the-art data sets for action localization? So you have currently relatively few, so this is one line of future work, which I'll get back to. Relatively simple data sets where you have simple actions, many sports actions. They're pretty small. Here, this is one of the bigger ones. UCF 101 with 24 classes for spatial temporal localization. And if you look now at the results, basically, you can see here that if you use the appearance, the handcrafted proposals, you can see that they perform significantly worse than if you extract appearance proposals or flow proposals. You can really see that they outperform these relatively simple proposals, and then depending on the data set, one or the other works slightly better, and then by combining the 2 sets of proposals together, you get a significant improvement in performance. And similarly, if you look here, if you use the features combined, so here you can see the results for using just RGB features. Here flow, what you can see here is that by stacking flows together, you can actually measure how the motion occurs over different frames. And then if you combine all this information together, you can see here that you significantly get a significant boost in performance. Okay, and then here, just a comparison. So what people use to measure the performance of action, spatial temporal action localization, they measure the overlap over the tubes. And here, basically, they use a threshold, so either 0.2 or 0.5. So 0.5 means that this intersection over union of the tubes is bigger than 0.5. And so here you can see that these are all state-of-the-art approaches which are based on CNN features, and you can see that this one performs, as is the case for object detection, with faster outperforms the other ones. This is true for all data sets. You can see that UCF 101 is a bit more difficult, particularly because it has this temporal localization inside the clips. Okay, and so this was kind of the state of the art on object localization. And so what is missing here is a better definition of how we take into account the temporal context, right? So here we have been just operating on the frame level, concatenating the information together, but we haven't really used the fact that we have video and we could actually extract information from the video. And so here, the idea is to go one step further and extract information of the video, just as a motivation. What I already said in the beginning, basically here, you don't know from one frame if the person is sitting up, down, or standing up. So if you have a frame-based approach, you wouldn't know this here. And so what you then do, if you link it together, you get some information, but ideally you would already want to infer from the start, in particular if you have just a small instance of time, you want to infer if the person is sitting down or standing up. Okay. And so here very clearly, if you have the neighboring frames, you can really see that the person is sitting down in the first row and standing up in the second row. Okay, and so what is the idea here? The idea here is actually to extend the idea of proposals or anchor boxes to anchor cuboids. So here the idea is, instead of having just a proposal in one frame, you want to have a tube proposal over a set of frames and use this to work on, okay? So your CNN will work directly on this anchor cube, okay? And so the anchor cube has to be has a fixed spatial extent over time, because you haven't decided where the object is in the sequence of frames. And once you have that, what you want to do is decide what's the action inside this anchor cuboid and how to regress the information to a better tubelet, right? So basically here you can see in light blue, you have the anchor cuboid, and then what you do is you regress to the shape of the object. So you learn how to regress, the same idea as for one frame, you learn how to regress, and this defines you actually in a better way the outline of the person, and you can really then do the regression over multiple frames jointly. Okay, and so how does the approach work? So here the approach is based on another state-of-the-art detector, which is the SSD detector, which actually works on these anchor boxes. So how does it work? It extracts a large number of anchor boxes per frame. So this on the left, you can just see briefly how it works. Here you extract a large number of anchor boxes per frame. Then you have a set of convolutional, here it's VGG layers, like in the next frame. And then on top of it, you have different outputs. So at different resolutions, you get an output, and you feed this into a classifier, right? So basically, this gives you the multi-scale approach, okay? So basically here, these are the different levels from which then the approach, the SSD approach, feeds into the network. So if you just look at this one thing, this would be the SSD detector. And so here, you can extend this relatively easily by defining an anchor box as the recurrent spatial location in this conf layer. So you can see here, for one layer, for the yellow layer, the final yellow layer, you can see here the blue dot indicates on which location we work in the image, and you can see that by taking the same position, it's actually the same corresponding position in the stack of frames, right? So very easily we can actually extract the recurring frames, the recurring information, and then we can feed this information here into the set of convolutional layers. So we can now apply over this stack of features, we can apply another set of convolutions, which then obtain us the classification and the regression. So from here, we then have a network which allows us to do classification and regression. And so here what we do is we regress jointly over the set of frames, right? And it gets as output the 4K output positions of the boxes in the frames, right? So we regress for all of them jointly. And we'll see in a moment that this gives much better results and for classification and for regression. Okay, here you can see again the anchor cuboid, and then after regression, you can really see that this regressed cuboid tube follows nicely the actor, so it really manages to learn the regression. Okay, and so basically one question is, how valid are these anchor boxes? Obviously they're not valid over the full length of the video, so it's only valid locally. So here, if you look, basically it's valid up to roughly, so this is recall at 0.5, so basically you look if these anchor cuboids overlap more than 0.5 threshold, and you can see here up to 10 frames, they're roughly valid. Okay, so up to 10 frames, the performance drop of the anchor cuboids is minimal, so you can really use them to regress. You don't to completely lose the object. And then if you look at the impact of the tube length, so here we have for RGB, flow, and diffusion of RGB and flow, and what you can see that it increases significantly. So this is per frame AP, again at overlap 0.5. You can see here that you get a really significant boost from 1 frame to 6 frames. Here, similar, after 6 frames, it kind of plateaus off. So basically a good compromise in complexity and efficiency is 6, and you can really see that the gain is significant. Another way of measuring how much improvement you get is by measuring the mean average overlap between the cuboids. So instead of just saying, I take the best one, which has an overlap of 0.5, I check how much they're overlapping and measure the overlap with the best matching tube, and you can see that the overlap increases significantly. So you go up by about 5 to 10%. Okay, so this means that your tubes get much more precise. And then similarly, you can also measure if you just use the tubes for classification, does the performance improve, yes or not? No. So here again, you can see that your classification performance also improves significantly. So you really get better classification score because you use these multiple frames together, and you get a better overlap. Okay, so here again, 0.6 is 6 frames is a good compromise. Okay, and then some example results. So you can see here, basically, you can see in red, that would be the examples that miss detection, so frames which are not detected, but boxes which are not detected if you just use 1 frame, and then if you extract it for the whole tublet, you see that you manage to find them all, and if you look at the scores are also more meaningful, right? So basically, in the case of k equals 6, you only have 2 scores, and the other ones you have each frame scored individually. Another example, so here it's the misclassification. The classification score is worse, so you can see here it flickers all the time, and if you look here, the action catch is classified correctly for the 6 frames. Okay, so for our results to the comparison of the state of the art, we use RGB and flow, late fusion, SSD with VGG 16th, and 6 input, k equals 6. And then for tublet linking, here we use a relatively simple linking strategy which is based on the maximum score and the overlap threshold. So if the tubelets are overlapping, here we use the overlap over the union of the tubelets, we actually then link them together. Okay, and then here, if we compare to the state of the art, you can see here the performance improves, in particular if you look at high overlap thresholds. So here basically you have the detector, the method, so basically here it's based on faster, here on SSD, and you can see at high overlap thresholds the performance improvement is enormous. So you really manage to get much better tubes. Here for JGBD similarly, we managed to improve the state of the art. And then here, UCF 101, which is the most difficult data set, you can see that for low overhead thresholds, we perform better than the state of the art by around 3%. And then if you move to higher overlap thresholds, the performance gain is really significant. So here, for example, at 0.75, so it means that the boxes are overlapping by 0.75, you can see that you get almost 20% improvement. And if you look at a few example results, so here you have the ground truths in green and the detections in yellow. These are different actions from the UCF 101 sports data set, and you can see that actually in some cases our detections are actually more precise than what they have as ground truth annotations. So it's quite precise. And so in the end, you can see here it follows nicely the motion of the person. And so here a few failure cases. So here, let me just stop this. What the problem was actually for the basketball player is that the person continues to be tracked even if the action stops. So given that it's just a point-wise detection, it continues. And then in the case of the two people performing this ice dancing, here the problem is that the two people get mixed together, and it actually doesn't manage to separate out them cleanly, because basically it's only a box detector. So what you would need here, the two things which are basically missing here, is a better mechanism for doing the tempo localization. And the second thing, you would need to have a better person model. So for example, if you would add human pose, something we're looking at, then you would be able to manage to dissect the two people and really recognize how they're interacting with each other. So this is something which we don't have yet. Okay, so we have seen that basically this new detector leverages the temporal continuity of the videos, gives us output tubelets, and which results in better scoring and localization of the detections. Okay, and then another line of work, so this is the tubelets, another line of work is actually how can you learn with sparse supervision, because if you want to create better data sets, we have seen that the data sets which we just looked at are very limited, and if you're going to create better data sets, you cannot annotate the human in every frame. So you want to learn this sparse supervision. And so here, the idea is, if we have the temporal extent given, what we do is we extract human tubes and use the sparse annotation to select the positive and negative human tubes and use those for training. And so actually what this shows is if the quality of the human tubes is very good, then basically what we will show, one frame or two frames is enough to select the positive and the negative tubes very well, and you're able to learn the detector very well. Okay, and so how does it work? The first step is the extraction of the human tubes. It builds on a faster Arsenic detector and human-specific detection, tracking by detection. So what we first do is we extract the humans and then track them through the frame. And the human detector is based, so what's important here, you have a good approach, but what's also important that you have this MPI human pose data set, which has 30,000 poses annotated. So you have a very large corpus of annotated poses, which you can use to train your human detector. And if you look at the performance, so here on these data sets, which we have seen before, it performs well, except on UCF 101, the resolution is very low, so it doesn't perform that well. And here on our new data set, which I'll present in a minute, again, the performance is high. And then obviously what we want to do, we want to have a better tracking approach. So far we have just seen tracking by linking, but this is very fun, very basic. And what you would want to do is to use also the information about the appearance of the person to learn your tracker, okay? And so what we do here is we have the human detector. In addition to that, we also learn an instance level detector on top of the features of the output of the features of the human detector. Okay, so the human detector, we use the last layer, the FC7 features, feed them in an SVM, use the positive instances to train the instance level detector, and use mining of negative examples in the same frame as negatives, right? So this allows us, we have the human detection, we start off with the best human detection in the whole video, and from there on we track backwards and forwards. We start there, we learn this instance level detector, right, based on the positive human detector and the negatives which are around it, and we then use the information, the joint information about the human and the instance level specific features to continue the track in the whole video. So we just use this one box and then use all neighboring frames. We decide where it could be found. So for the next frame, what we do, we perform a sliding window and search the best box according to the class level and the instance level detector. And then the next frame, as is the case in all tracking approaches, we update our instance level detector. And then once we have done this, we eliminate all the overlapping boxes and start with the second highest scored human detection in the video. And this gives us a small number of human tubes in the video. And if you look at the performance, so what's actually interesting here is the last row shows the baseline linking approach. So if the data set is easy, with not too much motion, for example, JHMBD, the people are mostly moving slowly and don't have any abrupt motions. Performance is comparable for all approaches, but if you look at UCF 101, where there's like rapid motions and it's more difficult data set where people can move out of the frame, etc., can really see is that by adding a tracker on top of the linking approach, you get a significant gain in performance, okay? And so what are the other variants which examined here? So here, the instance level is trained on different data sets. So here, ImageNet, Pascal, and MPI. And what's actually interesting to see is that by using the features which are the best possible features, as we know, it gives you actually a significant gain in performance. So here, we just take the last layer of a network trained on ImageNet, use that for the tracking, and you can actually see this results in a very poor performance. While if you use good features trained on humans, our tracking performance increases significantly. Okay, and then if we add the two of them together, the instance level detector and the human detector, we get a slight boost in performance, but actually just using this instance level tracker and starting from the best human bounding box detection works also very well, okay? So they're kind of equivalent. And then here just a few examples. You can see that basically even if the person is turning, taking pictures, appearing in strange poses, we're still able to track and detect the human tubes well. Okay, and then if we go to our sparse supervision, we can see here, so it's very simple, we only check if the tubes overlap significantly with the annotated frames. So the number of annotated frames runs from 1 to 5, okay? And we can see here that even with one annotated frame, our performance is already good, and by annotating a bit more, using a bit more annotated frames, the performance increases slightly, okay? And here, if you use exactly the same method with the ground truth annotations, you can see that, again, the performance is comparable. So here, obviously, we don't retrain the boxes, we just use the human detections for scoring. Okay, and so as I said before, existing data sets are all very limited. So basically, if you look at the actions and the length, there are UCF sports for 10 actions, then trimmed videos, so it's actually very short clips, 2 to 3 seconds, and in these very short clips you have to detect the action. So it's actually making the task much simpler. The same holds for JHMBD. And UCF Sport 101 is a bit more difficult, but again, the clips are almost trimmed, so there's not much temporal detection to be done, and the actions are very simple. So what we decided is to collect a data set with daily actions from YouTube. So the first point is that the videos are not trimmed. So the videos represent only a very small part the actions present only a very small part of the video, so you really have to do spatial and temporal localization. There can be multiple actions and actors per video, so it's not like as in the other data sets where it's one actor performing one action, and it's 31 hours of annotated videos. And we have annotated 5 keyframes per action instance. So for every action instance, so for every temporal window where there's an action occurring, we annotate 5 keyframes. And the videos are high resolution. And so there are 10 realistic actions, and they were collected to be quite similar, so that we have to really see in a fine-grained way how to distinguish them. And so basically what is there, for example, there's cleaning window, playing harmonica, brushing teeth, ironing, putting makeup on lips, and so forth. Okay, and so if we compare to the state of the art, the first part of the table compares the state of the art with weakly supervised methods. So there's not many approaches which do actually weakly or pointly supervised training on videos. So there's one approach which was published at ECCV 2016. So there they use points. They annotate in each frame 1 point. So that their number of annotations they use is much higher. And you can actually see here that our approach outperforms theirs significantly. And so the main reason is, so here what we did, we really re-implemented their features. So everything is the same except the annotations and the way we extract the tubes. So what they use to extract the basic elements which are fed into the classifier are spatial temporal agglomerations or superpixels. And then for these superpixels, they apply the trajectory features, okay? So the real reason why our approach works better is that the tubes are much more reliable. So basically the message here is that the human tubes are now very good, so we can really use them to perform this weak supervision. And then basically if you look here, our approach, if we feed in full supervision, it performs a bit better, but it basically performs on par as if you use weak supervision. And if you compare it to the other fully supervised approaches, the gap is actually not so significant, right? You can still see there's a gap between the best fully supervised method and this weakly supervised method. So basically we're still missing a bit of information due to the imprecision of these human tubes, but our results are, compared to what's around with weak supervision, very good. Okay, and so if you look at what we get here, so this is example results on the DALI dataset. Okay, so here on the top line, you can see our results. Below the ground truth, you can see that here the drinking action is mostly well detected, and the thing which is not completely precise is the temporal localization. So basically the precise starting point is not detected perfectly, and the same holds for the end point. But other than that, it's really detecting here that the guy is brushing his teeth and when he is brushing his teeth. And so why is this missing temporal detection difficult? It's basically because for now we just have a temporal sliding window which doesn't really measure the exact change when it moves from the state where there's not the action happening to the action. And the second point about temporal localization is also that it's not completely defined, right? You can see the guy is holding the toothbrush between brushing the teeth, and that kind of makes a difference. And so here, the idea how to be more precise in start and end times, again, would be based on the pose and the interaction with the object, right? If she's done with folding the textile, you can really see that her hands are not touching the textile anymore, and that would help you to improve the localization of the starting and end time. Yeah, and here you can see again there was this temple, and then here there's another, even more, this harmonica playing, where it's really hard to see if the guy has the object still in the hand or not, and then the temporal localization again doesn't work so well. Okay, and so basically in conclusion and some future directions, so basically we have seen that human tubes and tubelets first and then also tubes are very effective, work very well. What's missing is still a good definition of the temporal structure. So one approach which people are currently looking at is to use recurrent networks to integrate the temporal information over time, and to use that to have a better understanding of the beginning and end of an action. And if you look here, this is like some preliminary results. What you can see here in blue, this would be the ground truth, and then here the scores of an CNN. So it's really hard to determine precisely when the action starts and ends. And then here in green, you can see that if you use an RNN, so if you train a recurrent neural network, what it does, it takes as an input the information of the box, the classified box, the feature from which comes out of the classifier of the box. You take this into your recurrent architecture and propagate this over time. And so you can see here actually that this RNN helps you to localize the action much better. So here you can now really see when is the start and end point of the action, right? And so this is using exactly the same features as the method we have seen before. So no additional information, for example, about the hands or anything, but it just integrates the information over time, and this allows you to get a better localization, better temporal localization. Okay, another point which I mentioned is that basically what you want, you would want to design more accurate models. So what we have right now is just patches, and for these patches you want to classify if the action is performed or not. And so what the idea here is that basically if you add pose information and object information, you could significantly improve the performance of the spatial temporal localization. And so here, why would this start to work now? It's basically because approaches for 2D and 3D pose estimation starts to work reliable on real-world videos. So maybe 5 years ago, pose estimation algorithms were not very reliable, but now basically have very efficient 2D but also 3D pose estimation algorithms. So here, this is a result of one of our recent works on 3D human pose estimation. And you can see that it's not perfect, so it's extracted frame per frame. For now, there's no temporal information integrated. It's not perfect, but you can see that it is detecting the person, and even if it moves out of the frame, we can hallucinate the parts which are not visible. So we can really get an idea of what action the person is performing. And then another point is, basically, we designed the DALI data set. It was a lot of effort to annotate all this data, but it's still far from being a large-scale data set. So basically, it doesn't model all the possible actions. So it has 10 actions, and if you scale it up to 100, it's possible. But even 100 actions, you wouldn't have all actions and actums which are there in the world. And so another line of work which we're looking at currently is training based on synthetic data. So the idea here is we have humans, we have human body shapes, and we have mocap data. So we take the mocap data and render it under different viewpoints, under different lighting conditioning, with different clothes, in different environments. And this gives us our synthetic training data, right? So you can see here, maybe it's a bit hard to see, but basically you can see here that this data it's not perfect, but it's good enough to train in CNN, and it looks quite realistic. So what's still missing is the environment is not completely realistic, but the people are quite realistic. And if you look at what would you get if you train in CNN, the performance is very good, and you have this large quantity of data, right? So you can really generate data. You can take your mocap data and you can generate as much data as you want. So this is one idea of getting these larger data sets and use those to learn your actions. Another step towards more realistic data sets is actually to have a better definition. So this is like this is like manual annotation. So here the idea is really to design a vocabulary of all the basic actions, such as stand, walk, and bend, bow, sit. So get this dictionary of atomic actions and annotate them in a video corpus every 5 seconds. And this gives you another way of then maybe testing the approaches which you have obtained from the synthetic data. Okay, thank you for your attention.
Okay, any questions? У кого-нибудь? Да. Микрофон можете принести, пожалуйста?
Hello. When you compare tubes, do you compare it frame by frame or the whole tubes as an entity? So is there, which of the approaches for comparison do you use?
So in the papers we always do both, right? Frame by frame and then tubes. And so what I showed here, it was for the tubes basically, because that's kind of the final result which you want. You want to see how good your tubes are detected.
Yes, but what's the criterion of comparison of separate tubes? I mean, the ground truth tube and the detected tube. So there must be some overlap between them.
Yeah, there must be. So the criteria is that if you have per frame detections, you have an overlap, whatever, say 0.5, what you have seen, intersection over union must be bigger than 0.5. And the same thing you do over the video. So you do the same thing per frame and average it over the tube. So it's, I mean, it's exactly the same idea. And if you have a temporal localization, you multiply it by the extent of the temporal overlap, right? That's the formula.
Thank you. Thank you.
Please, what are hardware requirements and timing for this algorithm? Can it be run at real time or not?
So it depends a bit which ones, but they're close to real time. I mean, for example, the SSD detector runs at 30 frames per second.
Thank you.
Any more questions?
How do you think your work will work with lower frame rate? I don't know, maybe one frame per second, or 5, or even less.
So the question is, if you don't work on every frame but only 1 frame out of 5.
Yep.
I guess it depends. I haven't run the experiment, but I guess it depends largely on the video, right? If the motion is very fast, you'll miss something, and if it's not so fast, it will work perfectly fine, right? So I think it's really application dependent. I mean, you could just try it.
Any other questions? He'll speak Russian.
Hello, my name is Alexei. I'm not a specialist in machine vision. I'm a client of one of the projects in this area. So the objective is in the following. We have a big center in the bank, and we would like to realize similar system to analyze the work of our cash operators. So we have a certain behavior which is considered to be proper, and there is a behavior which is considered to be improper, and which can lead to some negative consequences. So you are giving us very simple examples in your presentation. So how, from your point of view, is it applicable in a more complex cases like ours? For example, when a door is being opened not by 2 keys but by 1 key, for example. Or when an employee should do a certain set of actions, standard actions, with the help of certain equipment or somehow else, but he behaves differently, or he gets distracted, or maybe he does some additional things, and many other things. There could be a zillion of examples where we can say that behavior is not standard and requires additional analysis.
Yeah, so basically the question was just to see if we can differentiate standard behavior from non-standard behavior. And I would say yes, definitely you can do it. The question is how subtle are the differences? But I guess, for example, if he hands out the cash or he screams or something, you can very well differentiate these different actions. Or if a robber comes into the bank and holds a pistol to the guy, it's also very clear you can detect it. So I think, yes, it would definitely apply, and it would even be simpler because in your bank case, you probably have a static camera, right? So you could have a static camera on the ceiling, and that would make things easier. So you could really see where the zones are which you're interested in, and then I think it would be quite straightforward to differentiate these different actions.
А если действия очень мелкие?
If the actions are very small and particular, with fingers or hands. In other words, when a person does some incorrect actions, he can turn his head away from camera or something else.
He can turn his head away?
Well, for example, he can turn his back to camera to hide some actions from camera. And this also could be a sign of bad behavior.
Yeah, right. I mean, basically you have to define what is bad behavior. Obviously, if you don't see what the person is doing, you cannot understand it, right? This is clear. But if you can obviously see if the person is turning around, and this is, I think what I said in the end is basically in this case, if you have the 3D pose, that's much more helpful, right? If you just have the outline, you might detect that it's a human, maybe it's the back or not, but if you have the 3D pose, you can really see that the person is turning around, and that would be like maybe a case where such type of approaches allow you to have a more finer analysis of the behavior. And again, if you have the human pose, you can also integrate the fingers, right? For example, there are approaches which actually like localize the fingers and things like that. So you could have the pose plus the fingers integrated over space-time.
Okay, so I think we have to move on. Maybe a very short last question, okay, but really short, and maybe Jean can come and change the laptop.
Your presentation. The meaning of every action, as the meaning of text, depends on the context and surrounding environment. So everything what is being done by a human person and how can we call his actions depends on dynamics and circumstances. Is that right? That's why the question is in the following. Do you take into consideration of what is happening around a person or any object which conducts these actions? Because only with this analysis you can understand the final meaning and can call it a certain specific action.
Yeah, so the question is basically, does the action depend on the context? Obviously, it does depend on the context. Context is up to some point already taken into account because you can combine this with the context features. But I think to answer your question, if you really want to analyze what's going on, you have to go one step further and move towards the 2D or 3D pose, right? Because now we have the localization of the point, the person, so there's a lot of things you can already do. But for example, between cutting an apple and cutting an orange or cutting something else, if you want to do this in a very fine-grained and very exhaustive way, then you have to move to something which is what I said in the end, like using the pose and the object interaction, and then you can really describe it.
Yeah, but let's imagine, you told us that a person has entered the bank with a gun. Let's imagine a situation that it's a real gun, or maybe it could be a game. How can we understand and differentiate one from another?
Well, I think the problem of differentiating a real gun from a toy gun, it's a problem even real policemen have, right? I mean, it's one of the classical things where the guy gets shot because he takes out a toy gun. So, I mean, there's some limits to differentiating a gun from a toy gun, but if you can train a classifier to differentiate different types of guns, that's totally possible, right? And then you had the performance of your approach, right? All these approaches, they're not yet perfect, right? So basically you have always this limit of how good it is, right? And this is the same thing if you have video surveillance, you can use these approaches today to help you detect things and like point the guy to it and alert him, but it's not perfect enough to have the thing run completely autonomous with any human intervention. It's the same thing, for example, for self-driving cars. They can alert you when a person is crossing, but it's not perfect enough to be sure 100% that it's always working. So.
Thank you very much.
Thank you.